Okay, let's unpack this. We're taking a deep dive today into a really interesting piece of tech called SSV, Secret Shared Validators.
Right.
Based on the overview you shared, our mission is basically to get our heads around this middle layer concept
Yeah, what it is, how it actually works.
and, why it even matters for decentralized networks.
Mm-hmm.
Think of it like getting a shortcut, maybe, to understanding how you can run something critical like a validator without
Mm-hmm.
one single person or entity ever holding the full key.
Which, I mean, that really changes the game for risk, doesn't it? Instead of one point of failure.
Exactly, you spread it out. So, okay, at its heart, what is SSV? The source describes it as, well, a pretty sophisticated system.
Yeah, it sits between the main network node, like a beacon node,
Yeah.
and the validator software itself.
The validator client.
Yeah.
And it's essentially running the validator operations for you.
Kind of, yeah,
Yeah.
on your behalf, but crucially, not in one single place or under one person's control.
Okay. And making that work, that distributed, trustless operation, must involve some clever tech.
Definitely. It uses some neat cryptography and coordination. That's where these core components come in. They work together to break down and share out the power of that single validator key.
Right, this is where it gets really interesting. The overview points to four main pieces. First up, how do you even start without a single key holder? That's distributed key generation, DKG.
Spot on. DKG is like the initial setup among the operators.
Yeah.
They all work together to generate the public key and the private key.
Okay.
But here's the kicker. No single operator ever sees the whole private key. Each one just gets a fraction, like a share,
Yeah.
of that private key. So right from the start, you've removed that central vulnerability.
Okay, that makes sense. So you've split the key, but then how do those individual parts, which can't sign anything alone, how do they actually come together to do something, like sign off on a block?
Good question. That brings us to Shamir's Secret Sharing,
Right.
and it's used alongside something called BLS signatures. Shamir's is a mathematical way to break a secret, the validator key here, into pieces or shares. And the magic is you don't need all the pieces to sort of use the secret collaboratively.
Yeah.
You just need a minimum number of threshold.
Like that formula, the new 3F plus 1 thing.
Exactly. That's just math specifying you need like more than 2/3 of the operators working correctly to overcome potential failures or bad actors.
Yeah.
The F
Got it.
and BLS signatures. They let the individual signatures from those shares be combined into one single valid signature as if the original key signed it, but crucially without ever actually putting the full key back together.
Okay. So Shamir splits it, BLS helps sign with the pieces. But how do the operators holding those pieces actually perform calculations or, agree on duties together securely without ever rebuilding the key?
Right, that's where multi-party computation, or MPC, comes into play.
MPC, okay.
Applying MPC lets those operators use their individual key shares to collaboratively compute things, like signing messages for validation duties. But the really powerful part is, the full validator key is never ever reconstructed on any single device during this whole process. It stays fragmented.
So it's like they're all contributing their bit to the calculation without revealing their own secret piece.
Precisely. And they don't see the full picture until the result is computed collectively.
Okay, that's clever. But for this group of operators to actually function like one validator, they need to agree on things, right? Like when to sign or what to sign. How does that coordination happen?
Yeah, they need their own internal consensus. SSV uses the Istanbul Byzantine fault tolerance consensus algorithm for that. IBFT.
IBFT, got it.
Think of IBFT as the internal operating system for that group, that SSV cluster. It makes sure they can all reach agreement on what the validator needs to do.
And Byzantine fault tolerant means it still works even if some operators are offline or acting weirdly.
Exactly. It's designed to keep functioning and reach consensus, even if a certain number of operators are faulty, slow, or even, malicious. It might randomly pick one operator's share to propose an action.
Okay.
And then a threshold of the others have to agree through this IBFT process before the action actually happens.
So if we pull back and look at the bigger picture, these four components, DKJ, Shamir BLS, MPC, and IBFT, they seem to build a system where the really critical stuff like key control and doing the validation tasks, it's all completely spread out.
Yeah, it fundamentally decentralizes control.
It's not just about making it more resilient if one part fails. It feels like a shift away from needing any single point of control at all.
Absolutely. You distribute the key, you distribute the operation, and you demand consensus from a majority before anything happens. That makes the whole validator operation inherently more robust, more fault-tolerant, and way more secure against, say, one operator getting hacked or going offline.
Okay, so wrapping this up, what's the big takeaway here? This dive into SSV, it really shows how combining some smart cryptography with consensus ideas can build this blueprint for, well, decentralized operations.
It allows these critical network jobs like validation to happen without anyone ever holding that single all-powerful key. It's about distributing the power and also the risk.
Right. So here's something to chew on, a final thought for you listening. If core network functions like this can be done collectively by a group using distributed secrets, what does that mean for our future ideas about owning digital assets or network governance or even digital identity? How might things change if we move away from relying on just one key held by one person or entity?